Good morning, stats guys, girls, everyone. Today we're going to finish up our section 8.3 day 2 with a formalization of the four-step process as we use it for the confidence interval for a mean. Simply put, we're going to take a look at how we find the confidence interval for a mean in everyday practice. So let's get started. How many states can you name in 1 minute? We will use this class as a random sample of AP students to estimate a 95% confidence interval for the mean number of states AP Stats student can name in 1 minute. So when the timer starts, list as many states as you can on a piece of paper and then write the number of states you listed on the board. Now, obviously, we can't really do that, so we're just going to take a look at data from a past year. What type of data is this? Categorical or quantitative? Well, the results that we are getting, the things that you're going to be answering this question with, are numbers. And those numbers have a meaning. In other words, the number 5 means something in relation to the number 12. So this leads me to answer this with, these are quantitative data. Next, we're going to enter the class data into Staplet, and then we're going to find the mean and standard deviation and sketch the dot plot of the sample data. Here's the results that we got from 1 year. We'll go ahead and copy and paste that over. And taking a look at our dot plot, this does kind of look mound-shaped. It's a pretty wide range. I don't know what happened with this one person who only got 4 states. Whatever. Let's just continue with this. Construct a 95% confidence interval for the number of states a senior can name, or I guess they mean an AP Stats students can name. Here's a 4-part plan again. We'll just kind of preview. We've got state, plan, do, and conclude, just like we did last time. To state, we need to talk about the parameter and the confidence level. So that's not really a big deal. In the plan part, we're supposed to put the name of the procedure. So we have only 1 sample. Because we're doing the confidence interval for a mean, it's going to be a t interval for mu. Remember, all of these name of the procedures are all kind of constructed in the same way. How many samples, what curve are you using, and then what is the parameter. So 1 sample t interval for a mean. Let's check our 3 conditions. I hope you remember what they are. Our first condition is the random condition. And we were told that this is a random sample by the question. For the 10% condition, we're going to take a look at our sample size, which is 23. We can see it up over here in the stats. And multiply that by 10, that's 230. And are there more than 230 AP Stats students? You bet. So we're just going to write 23 is less than 10% n. Capital N being the population size. Condition number 3 is a normal condition, which we can qualify in a couple of different ways. The first way is if the population is normal. And do we have anything here that says that the population of AP Stat students represents a normal population, or the number of states an AP Stat student can remember is a normal distribution? And there's nothing in the question that says it. So that's out. We can't use population as normal. The second way we could do it is if the sample size is large and our sample size isn't large. It's only 23. That's not bigger than 30. So we can't use the CLT to say that the sampling distribution is normal because we had a sample that wasn't bigger than 30. So what do we do? Actually, what we do is we revisit that first condition. Population is normal. And we revisit that because even though we weren't told that the population was normal, take a look at our sampling distribution, or our sample. Doesn't our sample look single-peaked and symmetric? Yeah, it does. So a sample that is reasonably normal or isn't non-normal is indicative of a population that is normal. In other words, we can infer that the population is normal because our sampling distribution doesn't look non-normal. So what we would write, population is normal, and we would say this is inferred because the sample has no strong skew nor outliers. And we happen to use a dot plot, so we're going to say that the sample dot plot has no strong skew or outliers. But you're free to use a histogram if you need to. Any of those would work. What also works would be a normal probability plot. If you remember, if the normal probability plot was linear, then that's indicative of a sample that is normal. But for us, I think the preferred way to do this is to look at either a dot plot or a histogram. And as long as there's no strong skew or outliers, then we can infer that the population is normal. And so, kind of shop talk time, you're only going to need to use this third method of showing the normal condition if you have a small sample, so you can make the dot plot easily, or if the dot plot is already provided for you. By far, this is kind of the least preferred method of showing normality, but it will happen from time to time. So remember, as long as the sample dot plot or the sample histogram doesn't show skew, or at least doesn't show a strong skew, it can show skew, it just can't show a strong skew. And if there's any outliers, if there are no outliers, then you can infer that the population is normal. That's what we're really after. We're inferring that the population is normal based on the sample. This brings us to the do section. So we're supposed to do the general formula, specific formula, plug in numbers, and then the answer. Okay, the general formula is the parameter is equal to the point estimate plus and minus a margin of error. We've got the specific formula is mu equals x bar plus or minus t star sx over root n. Now let's substitute some numbers here. Let's get the value of x bar, and x bar is, there we go, 12.826. Looking up at that chart again, I can see the standard deviation is 3.473 and n is 23. And then all that's left here is to find our t star. So let's grab our calculator. I'm going to go over to the distribution menu and do an inverse t. Our area is going to be 1/2 of 1 minus our confidence level, which is still 0.95. Our degree of freedom is the sample size 23 minus 1. And then we're just going to paste that. And that gives me 2.074. Never mind the negative sign. This is a t star, so it's always positive. One additional thing that you're going to want to write here is that you calculated the degree of freedom to be 22. That's going to be kind of important so that the critical value doesn't look like it materialized just out of thin air. Okay, crunching all those numbers together gives me a mu equal to 12.826 plus or minus 1.502. And the last thing we need to do here is conclude. Okay, let's call up our sentence frame and let's start substituting our numbers in. We are 95% confident that the interval from 11.324 to 14.328 captures the true average number of states that an AP Stat student can remember in a minute. Read it one more time for readability. We are 95% confident that the interval from 11.32 to 14.33 captures the true average number of states an AP Stat student can remember in a minute. Make a couple of adjustments here and then we're good to go. That is our interpretation. So a lot in common with that, the 4-step plan as it relates to proportions, isn't it? So much in common. Our important ideas, in fact, are almost exactly like the important ideas that we did for the 4-step process as it related to proportions. So we've got state, the parameter. This is different, it's mu, and it's the true mean of whatever the context is, and the confidence level. Things that I've kind of done in red, those are going to be changes or where this is different from the 4-step plan as it related to proportions. Step 2 of the 4-step process. This is going to be plan. So there are 2 things you need to do. You need to state the procedure, you need the name of the procedure, and then you also need the conditions. So the conditions are the same 3 conditions: random, 10%, and normal. The only real rub here is for the normal condition, you can satisfy that in one of 3 different ways: either normal population, a large sample, or an inferred normal population. So that normal condition is really a normal population or a large sample or an inferred normal population. Next, we have the do section. So you need the 4 things again: the general formula, the specific formula, substitute the numbers, and then what is the final interval. And then the 4th part of the 4-step process is to conclude, in which you interpret in context using the sentence frame. The sample size calculations are very similar again to what we did for the proportion of a population, except for the margin of error formula is a little bit different. If the t-star is unknown, you want to use a z-star instead. And of course, we know the standard error is the standard deviation of the sampling distribution. So with all of that under our belt, let's check our understanding. Administrators at your school want to estimate how much time students spend on homework on average in a typical day, typical week. They want to estimate mu with a 90% confidence level and a margin of error of at most 30 minutes. A pilot study indicates that the standard deviation of the time spent on homework per week is about 154 minutes. How many students are there going to need to be surveyed in order to meet that administrator's goal? So we start off with the margin of error formula, and we make sure that we want our margin of error to be 30 minutes, and then we're going to start substituting things. So the first thing we notice is that we're going to have to use z-star because we don't know what t-star is. Okay, now that we have our z-star, let's go ahead and substitute numbers. We know that Sx is, the pilot study indicates that the standard deviation of the time spent on homework is about 154 minutes. This is a 90% confidence interval. So our z-star for 90% is 1.645. Since we got all of this now, we're going to go into our solver so we can figure out our sample size. Okay, so math, Scroll to the bottom and get to solver. And the margin of error is equal to z. Now this part is wrong, so we're just going to have to delete this stuff. Oop, looks like we're going to have to get rid of everything. Okay, so z multiplied by the ratio of, okay, that didn't work, z multiplied by the ratio s over the square root of n. Okay. Now we're just going to put in our numbers. We want the margin of error to be 30. We know that our z star is 1.645. Our value of s, that was 154. And n is unknown. So let's put in a guess. A good guess here, typical guess, is 100. And then push alpha, enter. That gives me 71.3. Round up, so 72. There we go, 72. Next question. Biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made on the skin by an anesthetized newt. Here's the data from a random sample of 18 newts measured in micrometers per hour. Calculate and interpret a 95% confidence interval for the mean heal rate of mu. This sounds like the 4-step plan, and it is a 4-step plan. So the first part here is state. So mu is the true mean healing rate, and CL, or confidence level, is 95%. Next part is plan. And that is, let's refresh our memory. In the plan part, we need the name and then the conditions. So the name of this is going to be, this is a 1-sample t interval for mu. Remember, it's a t interval because we're computing mu. Condition 1 is random, and we are told that this is a random sample. And for the 10% rule, 18 is less than 10% of the number of newts. Remember, in order for that to be true, there just needs to be more than 180 newts. Guarantee there are more than 180 newts. Number 3 is a normal condition. So let's run through all the ways that we could satisfy this. The first way is with a normal population, and I didn't see that anywhere in the question, so we can't use normal population. The second way to fulfill this is with a large sample, and I think we're out of luck here too, because our sample size is only 18. So we can't use large sample either. Our last hope is that we can infer that the population is normal based on the sample. And to do this, we're going to use our calculator, and we're going to put all of our measurements into our calculator, all 18 of them, and then we're going to look at the histogram. So get over to your calculator. Start at the home screen, which will clear. Stat, edit, and it looks like I have stuff on my list, so I'm going to clear them. And now I'll start putting in our sample. Let's see, what is our sample? 29, 27, 34. And we just about have them all into our calculator. Now let's go to our stat plot menu, second y equals. Turn the first one on, set it to histogram, and this time we don't need a frequency list, so we're going to delete. And then zoom, stat, number 9, zoom stat. Whoa, problem. That's going to happen sometimes. Let's check to see where that problem is. And I'm going to go back to the stat plot menu. Yeah, I see what the problem is. I still have a frequency list here. So I think if I change that to 1, then that should work. Let's try it again. Zoom, stat. There we go. That's our histogram. Does that look like it has a strong skew? No. Does that look like has any outliers? No. Take a sketch of it. And then we'll finish the statement. The population is inferred normal because the histogram shows no strong skew nor outliers. Okay. Now this, a word about this and the histogram. Normally I would demand that you label the axes, that you give this a title, that you scale the axes appropriately. But in the context of the 4-part plan, this is just one of the tools. So you've got many more things to do than just the histogram. So in this case, it's okay just to leave a sketch of the histogram like we have here. This is the only time where it's going to be okay not to label your axes, not to give everything a title. So don't get ahead of yourself. Every other histogram you make still needs to be properly titled, proper axes, etc., etc. The next part of the 4-step plan is do. So we start with the general formula. The parameter is equal to the standard error plus or minus the margin of error. Then we go to this. We go to the specific formula. Mu is equal to x bar plus or minus t star sx over square root n. To do the substitution, you're going to need the summary statistics. So let's go back to our calculator and go to the home screen. And we're going to calculate one variable statistics for list 1. There is no frequency list, so I'm going to put a 1 there. And I'm going to my bad. I'm going to delete that. And then I'm going to calculate. There we go. X bar is 25.67 and SX is 8.32. N, of course, is 18. So we still need T star. So let's go back to our calculator. And we'll go to distribution, inverse T. And if I remember this correctly, we need a 95% confidence interval. So the area is still 0.5, 1 minus 0.95. Degree of freedom, well, this time our sample size is 18. So 18 minus 1 for our degree of freedom. And we'll paste that and hit it. 2.11. Back over on your paper, we're going to change T star to 2.11. And then next to it, we're going to write degree of freedom equals 17, because we want them to know that we actually calculated that and we needed to know that. And then finally, we're going to answer. So mu is equal to 25.67 plus or minus 4.14. Getting to the conclude part, let's copy and paste our sentence frame, and we'll start putting in our numbers. So we are 95% confident that the interval from 21.53 to 29.81 micrometers per hour captures the true mean of healing rate for newts. This is kind of a little bit of extra here. If this question is about newts, we better write the word Newt somewhere in our conclusion. So let's read this for, adjust this for readability. We are 95% confident that the interval from 21.53 to 29.81 micrometers per hour captures the true mean of healing rate for newts. That sounds a little bit awkward. I think we could fix this pretty simply though. Just by getting rid of the word of, that's going to read a little bit better. So the true mean heal rate for newts. And I think that's going to do it. So we've reached the end here. That was actually a lot more of this stuff than I probably anticipated at the beginning here. I thought we'd be in and out pretty quickly, but we weren't. There was a few new things, and really pay attention to the way that we did that check your understanding number 2. That's the way things need to go when you compute a confidence interval on your own. So that being said, this is the end of our chapter, chapter 8. So good luck to all of you studying for the chapter 8 test. Good luck to all of you on the chapter 8 test itself. And I'll see you next time for chapter 9. Have a good day.